Hello everyone, this is 𝐿𝐿 𝐶𝐻 and today I am back with another video in a series where we were discussing load management system, how they are designed at Uber. So till now we have created 3 videos in this series. In the first video we discussed QALM, quality of service, load management system. Then we discussed specific to Cinnamon, two description, two videos. In first video we discussed around high level idea of overall Cinnamon, and then in second video we discussed PID control. This is the third video and final video in this series where we will be discussing Cinnamon auto tuner. So this is one of the component, right? This was one of the component and we wanted to deep dive into the details of how we want to calculate that in-flight limit. So by the way, if you haven't seen the previous videos, do watch the videos. If you are not watching the videos, then just read through the blogs, okay? So that will help you to understand or like grasp the details from this video as well. So what we are discussing today, Cinnamon auto tuner adaptive concurrency in the wild, okay? Great great title. So the idea is that in the production traffic, how you are figuring out that in-flight limit so that you have multiple, or you can say different load wali services, right? One service has high load, one service has very low load, or like the request patterns can be very spiky, and so all those scenarios, right? So there can be multiple scenarios which can happen in the production, and what we have to ensure is our Cinnamon architecture should work out of the box without any inputs from the clients or the whatever internal services which Uber has, and again it should work out of the box. So let's discuss, and we will, as always, do the things from, or like do the description, or like read through the notes which I have created, and then try to understand whatever I understood. So let's start. Cool. So what is our motivation for the auto tuner? Motivation for auto tuner is figure out the in-flight limit, in-flight value. So whatever in-flight limit, basically in-flight limit is the number of requests that are has to be scheduled by the scheduler. So that is what we call as in-flight limit. So quickly summarizing on the architecture of Cinnamon, you do all those things. You ensure priority, which means that you check on if the priority is assigned to the request. If not, then you assign a default priority. Then you go to rejector. Rejector is like you do two things here. One thing is you verify that if the request has to be accepted or rejected. If it's accepted, then it is forward. If it's rejected, then it is rejected. PID control is the one component which provides the input around what should be the thresholds and all those things. Then if the request is accepted, it is added to the priority queue. Once it is added to the priority queue, then it is scheduled by the scheduler. Now scheduler maintains that number of, like, what is the number of requests that has to be processed, and that number of requests is basically called in-flight limit. Cool. And that number of requests, like how many number of requests that should be processed concurrently by a service, is figured out by AutoTuner, which we are discussing today. Great. So we are great with the summary. We are we are good with the summary now. So let's start and then go into the details. So the idea for Cinnamon is the service owners don't have to define the configurations, all those things which we did already, right? Between services, now the value can vary, right? Instead, we mentioned that we want to figure out it dynamically, and we already discussed that there can be varying loads and all those scenarios, right? So what are the different things which can happen? One is the between services. Some service has 1 rps, 1 request per second. Another service can be 1000 or 10,000 rps, okay? Cinnamon is going to work for all these services out of the box without any inputs from the users or the engineers or anyone. Within a service, so within a service, it is very highly probable that some of the endpoints serve high traffic and some of the endpoints are just maybe created for the operation purposes, right? So the traffic can vary within a service as well for specific to endpoint. Then between nodes of services, when I say nodes of the service, which means that a service don't always have to have similar kind of hardware. So if you are aware of a concept called auto scaling in AWS, so you can basically create auto scaling groups, and in each group, let's say you have two ASGs, right? Okay, in a, where your service is deployed, and one ASG is deployed with M4 or large instances. Another service, ASG is deployed with M4.x large or 4x large. So what I am trying to say is the load or the traffic which can be served by that particular node can vary. Okay, it is not a service agnostic, so it is can vary based on endpoint, it can vary based on service, it can also vary based on the hardware which the service is running on. Again, the last point is throughout the day. So a service, like there is a high possibility again, right, that a service will not have a same traffic throughout the day. If you talk about let's say booking the rides, and let's talk about India specifically, right? So there will be more rides within a day as compared to night. There will be some traffic in night as well, but during the day as well, let's say during the office times, there will be high traffic. Okay, everyone is trying to book a ride, or wo auto mil nahi raha, right? So these are the scenarios which you face. Our system has to figure out that limit which has to be solved by the system. So these are the all scenarios which can happen while we are trying to book a ride, or like any operations which Uber is performing, or any internal operations which are in progress. So that's the overall idea. Now we are trying to figure out what is the limit by the autotuner, right? So autotuner runs in background. We already discussed in our first video as well. These are the background process or daemon process which run in PID controller as well as autotuner. They run as a background process, so you are running a background go routine which keeps on updating the limit as and when required. Okay, and definitely as compared to as much similar to PID controller, it can also run, let's say every 500 millisecond, and then it can try to figure out. Okay, Autotuner compares the observed request processing latency with some reference latency and adjusts the in-flight limit accordingly. Logic is based on TCP Vegas algorithm. So TCP Vegas algorithm is a basically congestion control algorithm which is used in networking systems to help in avoiding congestions. Okay, so we will go into that in some time, but this specific line, autotuner compares the observed request processing latency with some reference latency. So when I say observed request latency, it's like you have sent the request, okay, and what is the time the request is taking. So when I say time, it is the like it moved out of the queue and then it was sent to the API handler. Okay, so what is the time the request takes for the processing? Okay, that's the observed request latency, and then we try to compare it with some reference latency. Okay, so if it's like taking more time then we should try to reduce some number of requests which service is processing, because we might think that okay, service is under load, so let's reduce the number of requests which are concurrently processed. Cool. Similarly, if the latency is very less, observed request latency is very less as compared to reference latency, then you can try to increase the in-flight limit. There are multiple nitpicks inside the architecture as well, how we will do it, but yeah, we will discuss all those, but the high level idea is this, and the logic is based on TCP Vegas algorithm as I mentioned. Now quickly summarizing on the idea, right? So you have inbound requests. This is your priority queue where you have request 1, request 2, request 3. Okay, then they are sent to a scheduler picks up the request which are in the priority queue. Based on the priority, we already have discussed in our previous video that every request has a assigned priority, which is combination of two things. One is tier, another is cohort. So every request has assigned tier, tier 0 to tier 5, and then it belongs to a particular cohort. Now from scheduler, this is passed to so the service for processing, and like whatever the number of requests that will be picked up by the scheduler is dependent on the in-flight limit, which is calculated by the autotuner based on TCP Vegas algorithm. Cool. Now TCP Vegas algorithm, what it is. So as specific to this video, okay, much specific to this video, we will only discuss whatever is relevant to this video only. Okay, what is relevant for the cinnamon. Do not treat this video as a reference to understand the entire network nitpicks. Okay, so I will give you a very high level idea about TCP Vegas, but if you are referring this video as a networking concept, you will might need to deep dive more into like other blogs and other videos which are more specific to TCP Vegas. But this video specifically will be more around how you modified the TCP Vegas algorithm and what are the different scenarios or edge cases which Cinnamon encountered and how they were fixed. Cool. So with this disclaimer, let's move forward. So TCP Vegas algorithm, as I mentioned, is a congestion control algorithm to improve the network performance. Okay. When I say network performance, let's take a quick example. Let's say, let's take an example of video streaming, okay, live video streaming. So let's say you have allocated bandwidth of 5 Mbps or Gbps or TB, whatever. Okay, so you have, let's say you have bandwidth allocated of 5 Mbps. Now what you have to ensure is, you have to ensure that you are trying to utilize that entire 5 Mbps of bandwidth. Okay, you are trying to utilize that entirety, and this is much similar to what you are trying to do in a service. You are trying to uh, ensure the maximum utilization of the service, right? So you are trying to ensure maximum utilization of service without avoiding the service going under load or unexpected scenarios, right? uh, and that's what we are trying into network as well. We are trying to ensure that the network is not congested. सब कुछ इकट्ठा नहीं हो रहा है कि भाई कुछ नहीं हो रहा, सब कुछ बावड़ा हो गया, ठीक है? तो what we are trying to ensure is this architecture of cinnamon is much similar to whatever happens in the network. In network we are trying to ensure that congestion do not happen, okay, and in here we are trying to ensure that service do not choke, basically. Cool. So in terms of, there are like much network related terms which I already explained to you. So what you are trying to ensure is proportion of total available bandwidth of network link used for data transmission. So whatever you are trying to ensure that you are, whatever link you have available, which like bandwidth, you can assume it as bandwidth. Okay, so whatever bandwidth you have available, you are trying to ensure that you are using as much as possible without creating a congestion scenario. Okay, and you also have to ensure the minimizing packet loss. So much similar to whatever we are trying to do here. Now the idea around what we are trying to do in architecture of cinnamon. So track, now we have moved out of the networking concepts. Okay, now we are trying to talk in terms of request, not in the terms of packet or like whatever that flowing through the network. We are trying to talk here in terms of the requests which are coming to the service. Okay, so what is the idea? So track how long a given request takes and compare it with the reference time. Great, this we already discussed, that whatever the time the request is taking, we will try to compare it with the reference time, and then accordingly we will make a decision. We have to increase the in-flight limit or we have to decrease the in-flight limit. Great. Okay, now let's say the current time taken is much greater than reference time. If it's equal to, okay, not exactly equal to, but it is like similar value in some time range. Okay, so let's say the time range or like the difference between the request is, let's say, only 5 microseconds, so we don't have to take any actions similarly. Okay, so current time taken is much greater than reference time, so service is loaded, so we will try to reduce the in-flight limit. Great. If the current time taken is much lesser than reference time, then what you are trying to do, use the service is underutilized, so we will increase the in-flight limit. Okay, very simple example. If it's much similar, then we have to do nothing. Our service is working great, it is in saturation kind of mode, and then we don't have to take any action, and in-flight limit can be kept as whatever it is right now, so you don't have to make any update operation. Now how TCP Vegas helps? So TCP Vegas will help in longer or smaller, how you will define it. Now whenever I say a reference time, okay, or whenever I say this greater than equal to, they say like how much greater. Okay, so I said that a current time taken is much greater than reference time. How much greater? Okay, is it 10 seconds, is it 100 seconds, is it whatever the time, like how will you figure out? So TCP Vegas will help in that. Longer or smaller, how you define it. Okay, now by how much should the in-flight limit be changed? Now I said that service is loaded, so reduce the in-flight limit, but by how much? We have to figure out that, right? You have to figure out a limit or a value by which the request or the in-flight limit has to be reduced. Cool, great. What is the reference time? We said that we compare it with the reference time, but what is this reference time? We mentioned that we are not asking the users or the clients to configure any values. Everything should happen dynamically out of the box without any inputs from any service owner. Cinnamon should figure out every configuration on its own, and then it should work out of the box to serve any kind of scenarios, any load which is served by the client service. So the TCP algorithm works on three things. One is target latency, which is called reference time. Okay, like we will try to compare with the target. So that is reference time. Then sample, the current observed latency, okay, the current observed limit which we discussed. Then inflight limit is the current limit, whatever the limit is set right now, and then we will try to update this based on these parameters. What's the algorithm? So what you are trying to do is you try to take the ratio of target latency and the sample along with current limit. So this graph will help you in that. And then based on what you do is you increase or decrease the limit based on queue size. A log function is used to smoothen the changes. We will again discuss this again. But the idea is, if you see this, right, if you see this graph, this particular graph, you have taken a ratio of sample and target latency, and then you try to do the comparison along with the inflight limit. And all those scenarios, if you want to see the exact algorithm, you can directly check out the Wikipedia article. But in here specific to this, what you are trying to do is you take the ratio of sample and target latency, and then try to along with the current inflight limit, and then do the smoothing of changes. The reason for doing, we will discuss that in a bit, okay, why we are doing the smoothing. So let's discuss how it will work with autotuner, okay, TCP Vegas algorithm. So let's talk in the context of autotuner, and then we will also discuss all these concepts here, whatever ratio we are taking, okay. Great, let's move forward. So uh, as per the blog, the Uber blog, it is specifically mentioned that this TCP Vegas algorithm might not work as it is for the Uber production services, okay, because there are very varying workloads which are served by the production service. So it's hard to come up with those configurations and then like manage the system overall depending on this algorithm. So we have to do some kind of tuning, and that's what we are going to discuss here. TCPS, TCPS, not TCP Vegas with autotuner. Great. So what are the different scenarios which can happen? Okay, and then we'll come with 3 resolutions, and then we'll discuss each of those resolutions in detail. So TCP Vegas with autotuner, loaded versus unloaded. Now loaded versus non-loaded. So performance of service is dependent on the load it is serving at the moment, okay. So take an example of it, right? uh, Same request will not take exactly same time every time. Let's say you are doing a get query, okay, so it will not take exactly the same time, okay, the time will vary. Now it can be dependent on any of the resources. Let's say your MySQL cluster which is used, okay, the DB which you are used, uh, there are some issues right now with this, okay. So the time taken is more. So the scenarios, this loaded or not loaded, they are not direct. They don't have to be directly depend on the query patterns or like the request number of requests which are served right now. It can also happen that same request sometimes takes more time as compared to other times. Great. So reference time recorded under no load can't be used for loaded scenarios. That's what I'm trying to say. Okay. Query pattern. Query pattern as in, so we have different APIs, okay. We mentioned that we try to tune this cinnamon framework depending on the API endpoints, and the APIs are not exactly same, right? Let's say it's a simple put request, so it will not return any data. Let's say it's a get call, so it might return a one row from the database. Let's say it's a get call but it returns a huge JSON payload, okay. So the payload which is returned by the API can highly vary. Bulky workloads. Now take a scenario of, let's say you are processing some batch workloads, so in a very small time you send lot of requests, okay. So let's say you run bulky workloads just 1 hour for a day, but the request in that time is highly what to say is high basically, which are served by the service, ever increasing latencies. This can also happen that reference time can be set to higher latency during long overloads, okay. So uh, this is one of the limitation or issue which can happen is that, let's say your load is increasing, so you will try to keep on increasing the reference time, okay. So this might create an issue. Non-overload service not always serve heavy traffic, leading to similar values of reference time and sample time. This can increase in-flight limit indefinitely. So let's say the traffic served is very less, okay. So in that scenarios it might happen that your service figures out that yeah, service is doing great, we can increase the inflight limit. Okay, and then it might happen that at reaching a certain point your service experiences a overload scenario. Okay, now in that scenario what you have to do is you have to decrease that inflight limit, but you have increased the inflight limit to such a limit so it becomes hard to quickly reduce that limit. Okay, and so it can create unexpected scenarios in the service which we want to avoid. Cinnamon base use case is that you are avoiding those unexpected and overload scenarios in the service. Great. So what are the resolutions for all these problems? Adjust the sample to not only a single value but actually representing a distribution. So instead of taking a single sample value, what we are trying to do, we will try to take a combination of multiple values and then try to do aggregation over it. Improve on how we reset the target latency. Okay, another thing is we will make the inflight limit bounded. Great. So it there will be defined minimum limit and max limit, min bound, max bound, and the inflight limit will be adjusted accordingly. Cool. Let's move forward with the details of all these things which you are trying to do. So first thing is latency sample. We will not take a single value from the sample, not a single observed latency we are taking. We are trying to take multiple values and then do aggregation and then use it. Okay, so you take an aggregate of latency. There is some algorithm mentioned in the blog. To be honest, I haven't gone through it, what it means and how it works, but if you want to try it out, you can directly do a search on internet and try to understand how it works. So the idea is that you take aggregate of the values, all the sample values, and then you collected the latencies over time interval for successful request. Okay, whatever the time is spent in processing the business logic, and we are not taking into consideration the time request is kept in the priority queue. Okay, we are only considering the time which request takes to process the request, process that business logic specifically. Okay, uh, and the interval. Okay, we mentioned that we will take aggregate. Now in how much interval? So what we want to do is we want minimum of 250 requests. Okay, so that our sample or our like aggregation has enough value so that we get a good reference number. Okay, so the time frame is depending on the request throughput. It varies from 2 to 30 seconds, and it is adjusted automatically depending on whatever throughput the service is serving. Okay, the minimum we have to ensure that minimum 250 requests in the interval. Then we take a percentile. So P90 is used. Again, these things are figured out based on the load testing. So P90 is used in some of the scenarios. P85 or P80 is also used. But again, it depends on the use case and the Cinnamon tries to figure out. But in maximum scenarios, P90 works for the services. Then you smoothen the percentile. For smoothing the percentile, what you use is exponential smoothing mechanism. It's algorithm. If I talk about smoothing, right, we also use this word sometime back in this video. So what does smoothing means? So we are saying that we are taking 250 samples or 250 inputs, right, in a particular but in a single aggregation. Now we want to avoid anomalies. Okay, so that's the reason we are also taking P90, right? So what we are trying to do is we are trying to reduce that noise. Okay, we are trying to come up with a particular value and we want to exclude any noise created in the requests. Okay, some requests, let's say, took 30 seconds, so we want to avoid that, taking avoid taking that, so that we actually get a good enough value to do our analysis. So smoothing is done on time series data and is used to reduce the noise fluctuation in the data, whatever I described right now. Remove the data irregularities and make it easy to analyze. Great, that's the definition of smoothing. But the idea is that you remove the anomalies and then take the sample which are not anomaly in our entire aggregation. Periodic reset of target latency. This is one of the things, right? We want to adjust or like reset the target latency from time to time. So target latency should be constant in ideal scenarios, but we are not living in ideal world. So we have to reset from time to time, but this is not the case with production environment. We highly agree with this. Target latency is use the lowest recorded sample, observe the target latency and periodically send it. So this could be the basic idea, like how will you set a target latency. So what you can do is in that 250 request which you taken, take the latency which is lowest, okay, and then use it as a reference. There is also like a link attached to this blog itself which redirects to Netflix repository, which is concurrency hyphen limits, I guess, which uses the similar approach. Okay, so in that what you do is you use the lowest recorded sample observed at target latency and periodically reset it. Okay, so in that particular time frame you check the lowest one and then use it as a reference. What issue it cause? What issue it can cause? What's the issue? During long overloads, it leads to ever increasing target latency and then ever increasing in-flight limit. So let's say our latencies or like our requests are taking too much time. Okay, so in those scenarios, the lowest value as well, whatever the lowest value are taking, it can be also high, right? So in those scenarios, the reference will keep on increasing. How? So let's say your latency was earlier 5 seconds. 5 seconds is a very high number, but for example sake, okay, so let's say the request is taking 5 seconds. Now this is the lowest time right now in, let's say, 5 seconds, 6 seconds, 7 seconds. There are multiple requests and 5 seconds is the lowest. So you set the reference as 5 because, but the load is high on the service. So now you are comparing the 5 second. Now a new request came in. Okay, so let's say it's 6 second. Okay, so in those scenarios your request time or your reference time will keep on increasing in the overload scenarios. And again, a similar thing can happen that it will keep on increasing, and we have to make that bounded, right? Or not bounded, but what you say, our reference value should be such that your requests are not taking too much of the time to process. Okay, they should be processed in the some time frame, that your service is not overloaded, as well as customers are not hampered, that customers are waiting for a request and they are not getting any reference because your service thinks that everything is fine. So during long overload, it can lead to ever increasing target latency. The reason is the value is set to latest value under load, and there is possibility that it will not reduce because service is already under load, which we already mentioned. Uh, so what is the solution? There is a problem, there is an issue. We are not taking a very default approach. So covariance is a solution. So covariance is a statistic concept. What it tells is it tries compare two values. Okay, it tries to compare two variables, covariance as in like variables which exist, which coexist. Okay, so it tries to compare those two variables and check their directions, if they are moving in the same direction, or they are moving in the opposite direction, or they are moving in some random direction. So we are interested in if the covariance is positive or if the covariance is negative. Okay, so covariance helps you, tells you whether two variables move in the same direction, which is positive correlation, or if they are moving in the opposite direction, which means that there is a negative correlation. So increasing in-flight limit leads to a higher throughput, which is good, which means covariance is positive. Okay, or increasing in-flight limit leads to a lower throughput, which means covariance is negative. Okay, so and how you like how much data points you take for this covariance calculation? Covariance is calculated for last 50 intervals, and in-flight limit is increased decreased based on if it's positive or negative. Okay, so if it's positive, then it's increased. Yeah, it's increased, and if it's negative, then it is decreased. Cool, great. Last point is we want to ensure the in-flight limit is bounded. Okay, it should not happen. Again, this issue which we already discussed, right? You have increased the in-flight limits to a high value, and then overload happens, and then it becomes hard to decrease that limit quickly. Okay, so to ensure that, what we try to do is uh, we make the request, or like we make the limit bounded. Now what is the limit? What's the max limit? So the max limit is whatever the in-flight limit is right now. So let's say is 5. So your max limit, or like number of maximum number it can go to, will be 5 into 10, which is 50. Okay, lower bound will be number of CPU cores assigned to a service. So if let's say the service is running at 4 CPU cores, so the lower bound will be 4. You can assume that a single request is processed by one CPU core. So yeah, great. So this is all about our Cinnamon architecture. We discussed and we covered 4 videos in the load setting management system QALM, then in the 3 videos of Cinnamon. I hope you understood all the concepts. Leave any comments if you any things were doubtful, and we will meet again with the new concepts and new engineering blocks and new architectures from different companies. Till then, stay safe. Tata. Bye bye.